So here are the answers to the questions at the end of the previous chapter. Hopefully you've got all these right. So why don't you tick these off before we go on to reflection, refraction and diffraction. Reflection in a plane mirror. Now plane in this instance means flat, so it's reflection in a flat mirror. The incident ray is the light ray that hits the mirror, and the reflected ray is the one that bounces off. Now we use this term the normal a lot in reflection. The normal is the imaginary line which is perpendicular to the mirror. And reflections in plane mirrors produce images which are virtual, come on to that in a minute. They're upright, in other words it's not turned upside down, and they are laterally inverted. They're turned about the y-axis or they're spun around 180 degrees from side to side. And you'll see this is how you draw a ray diagram. You'll see that we have the incident ray coming in from the left. It hits the mirror. It's then reflected. We have the reflected ray. You'll see that I've labelled the two angles I, this is the angle of incidence, and R, which is the angle of reflection. And going up and down through the middle, that perpendicular line is called the normal. And that's where all angles are measured from. I equals R, the angle of incidence equals the angle of reflection. Now when you draw a ray diagram in the exam, always draw the arrows in the correct direction. The angles I and R must be equal, and the ray must touch the mirror. Don't cut it short and bounce it off something in mid-air. Virtual and real images. We just mentioned that reflections in plane mirrors are virtual images. Now a real image is one that's formed where real rays cross. A virtual image, one like the image in the mirror, where the image seems to be coming from behind the mirror. The image is formed by imaginary rays crossing. So here I'm forming a real image. I'm projecting real rays onto a screen. The image is formed on the screen at the point where the real rays cross. That's a real image. And this is a virtual image. The rays seem to be coming from behind the mirror, and the object seems to be behind the mirror. Well, it's not really there, and the rays aren't really coming through the mirror. So these are imaginary rays. So the virtual image is formed where the imaginary rays cross. So how do you draw the light rays and the imaginary rays when it's reflection in a plane mirror? Well, remember that the rays are actually reflecting from the surface of a mirror. So you can see at the surface of the mirror I've got two rays there. There are arrows on those lines going in the right direction. I've drawn the normal, which is the perpendicular line, and the angle of reflection is equal to the angle of incidence. But my image is the same distance behind the mirror as the object is in front. So I've carried on the light rays from the surface of the mirror to go all the way back to the image which is behind the mirror, and I've drawn those in dotted lines. So what's refraction? Now this is the change in direction of light as it passes from one medium into another. For example, as it passes from the air into glass or into water. Now if the rays are travelling along the normal, they're not affected by refraction. Now the angle of refraction is measured between the normal and the refracted ray. So this diagram shows refraction through a glass block, and you can see that the rays when they're in air, are parallel. The ray that emerges from the glass block is parallel to the ray that goes into the glass block. It's just displaced to the side slightly. So there's a good rule of thumb, it's a good guidance. The rays that go into the glass block and that emerge ought to be parallel but displaced. Now light refracts towards the normal when it's passing from air into glass, or when it's passing from a less dense medium into a more dense medium, and it refracts away from the normal when it's passing from glass into air, or when it's passing from any more dense medium into a less dense medium. Diffraction. Now this is the spreading out of waves as they pass through a gap or as they move past an object. The narrower the gap, the greater the spreading out, but the wave fronts remain the same distance apart. The closer the wavelength is to the size of the gap or the object, the greater the diffraction. So these diagrams show diffraction through a narrow gap and through a wide gap. You can see that the effect is greater when the gap is narrow. Now the diffracted wave fronts, the ones that have passed through the gap and come out the other side, should be semicircular, equidistant, and the same distance apart as the incident wave fronts. That's how you should draw them. Now, how are TV and radio signals affected by diffraction? Well, if you live in a hilly area, then the longer wavelength signals, that's the TV signals, may be affected by diffraction, whereas the shorter wavelengths, for example radio, are not. Okay, so quickly test yourself. Hopefully you've printed out all these notes so you can answer it now and find the answers at the beginning of the next chapter.